Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The story of William Sealey Gosset is inextricably linked to the frothy head of a pint of Guinness. He was, first and foremost, a statistician employed by the famed Irish brewery, a position that might seem an unusual crucible for groundbreaking statistical innovation. Yet, it was within the walls of St. James's Gate Brewery that Gosset confronted a problem of profound practical consequence: how to conduct reliable statistical tests when sample sizes were necessarily small. Brewing, even with centuries of tradition behind it, relies on quantifiable processes. Variables such as barley quality, hop bitterness, fermentation temperature, and yeast strains all contribute to the final product's characteristics. Experimentation is crucial for optimizing these variables, but large-scale trials are often impractical, expensive, and time-consuming. Imagine the logistical and financial burden of testing hundreds of different barley varieties across multiple growing seasons and fermentation batches. Gosset's challenge resided in extracting meaningful insights from limited data, a situation removed from the idealized world of asymptotic theory favored by many statisticians of his day. Adding another layer of complexity, Gosset published his statistical work under the pseudonym student. Guinness, like many businesses, closely guarded its trade secrets, publishing under his own name, risked revealing commercially sensitive information about brewing processes or barley sourcing. This cloak of anonymity, while born from corporate necessity, has added a touch of mystique to his legacy. The name student is now synonymous with a pivotal contribution to statistical inference, a contribution born from the very practical needs of a brewery. His initial forays into statistical analysis at Guinness involved examining barley yields. The goal was straightforward: to identify the barley varieties best suited for malting, the process of converting barley into fermentable sugars. This seemingly simple task presented a significant statistical hurdle. Farmers cultivate countless varieties of barley, each exhibiting unique characteristics. Evaluating each variety thoroughly would demand extensive field trials, a proposition that strained resources and time. The brewery needed to make informed decisions based on relatively small samples of data gathered from these trials. These constraints forced Gosset to grapple with the inherent uncertainty of small sample statistics. The core problem Gosset addressed was the accurate estimation of population parameters, such as the mean and variance, when only small samples were available. Classical statistical methods, largely built upon the assumption of large sample sizes, often proved inadequate in these scenarios. For example, relying on the normal distribution to construct confidence intervals for the population mean becomes problematic when the sample size is small and the population standard deviation is unknown. Estimating the standard deviation from the sample introduces additional uncertainty, which the normal distribution fails to account for adequately. This is where Gosset's genius came into play. He recognized the limitations of existing methods and embarked on a quest to develop a more appropriate statistical tool. This essay seeks to illuminate the genesis, methodology, and enduring impact of William Sealey Gosset's statistical contributions. It will explore how he transformed a practical problem in brewing into a fundamental advancement in statistical theory. His work provided a rigorous framework for drawing inferences from small samples, a challenge that continues to resonate across diverse fields, from medical research to quality control. Gosset's statistical journey was not without its challenges. He initially sought guidance from Carl Pearson, a towering figure in the field of statistics and the founder of biometrics. Pearson, however, remained skeptical of the need for specialized methods for small samples. Pearson's intellectual focus rested firmly upon large sample theory and asymptotic approximations. Convincing Pearson of the practical importance of small sample statistics proved to be an uphill battle for Gosset. Despite Pearson's initial reservations, Gosset persevered, driven by the pressing need to solve real-world problems at the brewery. He possessed a unique blend of theoretical understanding and practical insight, allowing him to bridge the gap between statistical abstraction and empirical application. The limitations of relying on the normal distribution with small samples became apparent to Gosset through his work with barley. Imagine trying to determine whether a new barley variety produces a significantly higher yield than a standard variety based on data from only a few test plots. If the sample size is small, the estimated sample variance may be a poor reflection of the true population variance. This can lead to inaccurate confidence intervals and unreliable hypothesis tests. Gosset understood that the distribution of the sample mean, when the population standard deviation is estimated from the sample, deviates from the normal distribution, especially when the sample size is small. The practical implications of this deviation are substantial. Using the normal distribution when it is inappropriate can lead to an overestimation of statistical significance. A researcher might conclude that there is a real difference between two groups when, in reality, the observed difference is simply due to random sampling variation. This type of error can have serious consequences, particularly in fields such as medicine, where decisions about patient treatment are often based on statistical evidence. Gosset's work provided a way to avoid these errors by using a more appropriate distribution, one that accounts for the added uncertainty associated with small sample sizes. Gosset's statistical work at Guinness was undeniably influenced by the intellectual environment of the time, particularly the work of statisticians like Carl Pearson. Pearson's contributions to correlation, regression, and the chi-squared test provided a foundation for statistical inference. However, Gosset's unique contribution lay in his ability to recognize the limitations of these methods when applied to small samples. He saw a critical need for a statistical tool that could handle the inherent uncertainty of limited data, a tool that would ultimately become known as the t-distribution. He was influenced by the work of Arthur Lyon Bowley, particularly his asterisk elements of statistics asterisk, which provided a clear and accessible introduction to statistical methods. Bowley's emphasis on the practical application of statistics resonated with Gosset's own focus on solving real-world problems. The development of the t-distribution marked a significant departure from the prevailing statistical orthodoxy. It provided a more accurate way to calculate confidence intervals and conduct hypothesis tests when the population standard deviation is unknown and must be estimated from the sample. This innovation had a profound impact on a wide range of fields, enabling researchers to draw more reliable conclusions from small data sets. From agricultural research to clinical trials, the t-distribution became an indispensable tool for making informed decisions in the face of uncertainty uncertainty. The t-distribution addresses the problem of how the uncertainty in estimating the population standard deviation from the sample affects the distribution of the sample mean. The t-distribution has heavier tails than the normal distribution, reflecting the increased probability of observing extreme values when the sample size is small. Gosset's deep immersion in the practical realities of brewing led him to confront a statistical challenge largely ignored by the theoretical statisticians of his day. He needed to assess the quality of barley and other ingredients using very small samples. Traditional statistical methods, heavily reliant on large sample sizes and the assumption of a known population standard deviation, proved inadequate for his purposes. When dealing with small samples, the standard deviation is estimated from the sample itself, introducing additional uncertainty that the normal distribution fails to account for. This problem became the central focus of his groundbreaking work. Gosset adopted an empirical approach, a hallmark of his pragmatic mindset. He sought to understand the behavior of sample means from small populations to extensive simulations and physical experimentation. Imagine Gosset painstakingly drawing samples from a known population, perhaps represented by index cards each bearing a numerical value. He would repeatedly draw small samples, calculate the mean and standard deviation for each, and then meticulously record the distribution of these sample means. This hands-on approach allowed him to observe firsthand how the distribution deviated from the familiar bell curve of the normal distribution as sample sizes dwindle. Author Leon Bully's Elements of Statistics significantly influenced Gosset's early understanding of statistical methods, providing a foundation upon which he built his innovative approach. Bully's work offered a comprehensive overview of statistical techniques, shaping Gosset's initial perspective. The critical issue Gosset addressed was the impact of estimating the population standard deviation from the sample itself. When the true population standard deviation is known, the distribution of the sample mean follows a normal distribution, a concept well established in statistical theory. However, in practical situations, the population standard deviation is rarely known and must be estimated from the sample data. This estimation introduces additional variability, particularly with small samples, causing the distribution of the sample mean to deviate from normality. Gosset recognized that ignoring this additional uncertainty could lead to inaccurate conclusions and flawed decision-making. His experimental process involved calculating the sample standard deviation and carefully observing its effect on the distribution of the sample mean. He noted that as the sample size decreased, the distribution became more spread out, with heavier tails than the normal distribution. These heavier tails indicated a higher probability of observing extreme values, a crucial consideration when making inferences based on small samples. The culmination of Gosset's work was his 1908 paper, The Probable Error of a Mean *, published under the pseudonym *Student*. This seminal paper introduced the t-distribution, a probability distribution specifically designed to account for the uncertainty in estimating the population standard deviation from small samples. *Student's paper detailed the shape and properties of the t-distribution, highlighting its key differences from the normal distribution. He demonstrated that the t-distribution is symmetrical and bell-shaped, similar to the normal distribution, but with heavier tails. The degree of these heavier tails depends on the sample size. Smaller samples result in more pronounced tails. Gosset's work was deeply rooted in the statistical framework established by Carl Pearson, particularly Pearson's work on moments and curve fitting. He utilized Pearson's methods as a starting point for characterizing the distribution of the sample mean. However, Gosset diverged from Pearson's emphasis on large sample theory, recognizing its limitations in addressing the practical problems he faced in the brewery. Characterizing the t-distribution analytically presented significant mathematical challenges. Gosset faced the task of finding a mathematical function that accurately described the observed distribution of sample means. He employed mathematical approximations to overcome these difficulties, carefully balancing accuracy with computational feasibility. While he lacked a complete analytical derivation, his empirical approach provided strong evidence for the validity of the t-distribution. The novelty of Gosset's approach lay in its unique combination of empirical simulation and mathematical reasoning. He didn't solely rely on theoretical derivations. Instead, he grounded his work in real-world observations and experimentation. This pragmatic approach allowed him to develop a statistical tool that was both theoretically sound and practically useful. By physically drawing samples and meticulously analyzing the results, he gained a deep understanding of the behavior of sample means, paving the way for the t-distribution. The t-distribution's heavier tails directly address the problem of increased uncertainty when estimating the population standard deviation from the sample. This heavier tail characteristic reflects a higher probability of observing extreme values compared to what would be expected under the normal distribution. Consequently, when using the t-distribution, statistical tests become more conservative, reducing the likelihood of falsely rejecting the null hypothesis, a critical consideration in scientific research. Gosset's t-distribution directly influenced Ronald Elmer Fisher, who subsequently provided a rigorous mathematical foundation and generalized the concept through the introduction of degrees of freedom. Fisher's work solidified the t-distribution's place as a cornerstone of statistical inference. The implications of Gosset's work extended far beyond the brewery walls. By providing a reliable method for analyzing small samples, he empowered researchers in various fields to draw more accurate conclusions from limited data. This innovation proved especially valuable in areas where collecting large samples is impractical or impossible, such as in medical research or agricultural experiments. The t-distribution remains a fundamental tool in statistical analysis, widely used in hypothesis testing, confidence interval estimation, and regression analysis. Its enduring relevance underscores the importance of Gosset's contribution to the field of statistics. The t-distribution serves as a constant reminder that statistical methods must be adapted to the specific characteristics of the data and the research question at hand. The evolution of Gosset's work, however, did not occur in a vacuum. It benefited significantly from the insights and rigor of R.A. Fisher, a figure who would become a towering presence in the development of modern statistics. Fisher's engagement with Gosset's findings was crucial in solidifying the t-distribution's mathematical foundations and ensuring its broader acceptance within the scientific community. Their interaction though initially marked by some resistance from other prominent statisticians, ultimately fostered a deeper understanding of the t-distribution's properties and its applicability across diverse fields. Initial reception to Gosset's work, particularly by Carl Pearson, was marked by a degree of skepticism. Pearson, a dominant force in statistical circles at the time, had a preference for large sample methods and a reluctance to embrace techniques designed for small data sets. He questioned the generalizability of Gosset's findings, a concern that stemmed from the empirical nature of Gosset's initial derivation. Gosset's approach, relying on extensive simulations and empirical observation, lacked the formal mathematical proof that Pearson, and many others, deemed necessary for widespread acceptance. This is where Fisher's contributions proved pivotal. Fisher, a brilliant mathematician with a profound understanding of probability and statistical inference, recognized the significance of Gosset's work. He saw the potential of the t-distribution to revolutionize statistical analysis, especially in situations where sample sizes were limited. He undertook the task of providing a rigorous mathematical foundation for Gosset's empirical results. Fisher's approach involved deriving the probability density function of the t-distribution from first principles, using methods of mathematical analysis that were far more sophisticated than those available to Gosset. A cornerstone of Fisher's contribution was the formalization of the concept of degrees of freedom. Gosset had intuitively understood the need to adjust for the number of parameters estimated from the sample data, but Fisher provided a precise mathematical definition and a clear explanation of its role in the t-distribution. Degrees of freedom, in Fisher's formulation, represented the number of independent pieces of information available to estimate a parameter. This insight proved crucial in generalizing the t-distribution and making it applicable to a wider range of statistical problems. The degrees of freedom parameter elegantly captured the impact of sample size on the distribution's shape, allowing for more accurate inferences from small samples. Fisher's mathematical derivation of the t-distribution's probability density function involved several sophisticated techniques. He utilized methods of calculus, including integration and differential equations, to determine the exact form of the distribution. He also employed the concept of sufficiency, a principle that allows one to focus on the essential information contained in the data, thereby simplifying the analysis. Fisher's work provided a complete, mathematically rigorous description of the t-distribution, including its mean, variance, and other key properties. This formalization provided researchers with the confidence to apply the t-test, a statistical test based on the t-distribution, to their data, knowing that its properties were well defined and understood. Fisher's work on the t-distribution culminated in several key publications that brought Gosset's ideas into the mainstream of statistical thought. In his 1925 paper, Applications of Students' Distribution, published in ***, Fisher provided a detailed derivation of the t-distribution, including the formula for its probability density function. He also presented the t-test, along with clear instructions on its use. This publication served as a definitive guide to the application of the t-distribution, and it played a crucial role in popularizing Gosset's work. Fisher's 1926 book, **Statistical Methods for Research Workers**, further elaborated on the t-test, providing numerous examples and illustrations of its use in various scientific fields. This book became a standard text for statisticians and researchers, and it ensured that Gosset's work would be widely disseminated and adopted. Fisher also acknowledged Gosset's contributions explicitly, giving him due credit for the initial discovery. The impact of Fisher's work extended beyond the mathematical formalization of the t-distribution. His insights facilitated the widespread adoption of the t-test, which became a fundamental tool for statistical inference. The t-test allowed researchers to compare the means of two groups, test hypotheses about population means, and assess the significance of regression coefficients. This had a profound impact on fields such as medicine, agriculture, and engineering, where the t-test enabled researchers to draw more reliable conclusions from limited data. The relationship between Gosset and Fisher, though primarily conducted through correspondence, was a collaborative one. Fisher, while providing the mathematical rigor, frequently sought Gosset's insights and practical experience. The collaboration, though it may appear to be a one-sided affair, with Fisher providing all the mathematical backing, was a true partnership. Fisher, in developing his theoretical framework, often sought Gosset's input on applications and practical interpretations. Gosset, in turn, benefited from Fisher's mathematical expertise, which helped him refine his understanding of the t-distribution and its properties. This interplay of theoretical and practical knowledge proved to be a powerful catalyst for the advancement of statistical science. The refinement of Gosset's original formulation through Fisher's insight of degrees of freedom made the t-distribution more generally applicable. Gosset's initial derivation catered to specific situations, particularly those encountered in brewing. Fisher's mathematical framework allowed for the adaptation of the t-test to a much broader range of scenarios. The degrees of freedom parameter facilitated the use of the t-test in settings involving varying sample sizes and different experimental designs. This flexibility made the t-test an invaluable tool for researchers across diverse disciplines. Fisher's work on the t-distribution, therefore, represents a crucial turning point in the history of statistics. He provided the mathematical framework and the theoretical underpinnings that transformed Gosset's empirical findings into a widely accepted and universally applicable statistical tool. The collaborative spirit between the two men, with Fisher building upon Gosset's initial insights, exemplifies the power of scientific collaboration and the importance of both theoretical rigor and practical experience in driving scientific progress. The t-distribution, a testament to their combined efforts, remains a cornerstone of statistical analysis, a tool that continues to empower researchers to make informed decisions based on data, even when the data is limited. The legacy of this partnership is a constant reminder of the profound impact that can be achieved when theoretical brilliance is coupled with practical ingenuity. Gosset's impact, however, extended beyond the theoretical elegance of the t-distribution. He demonstrated an extraordinary aptitude for designing experiments, particularly in the context of agricultural research. His work at Guinness, while intrinsically linked to brewing provided a fertile ground for developing and refining methods of experimental design that would prove invaluable across a wide range of scientific disciplines. The challenges inherent in agricultural research, such as spatial variability in fields and the limitations imposed by available resources, demanded innovative approaches. Gosset responded by devising methods to extract the maximum amount of information from the data he could collect. The practical problem Gosset faced was clear: how to determine the optimal conditions for growing barley, the primary ingredient in Guinness stout. The quality of the barley, and thus the ultimate quality of the beer, was subject to a multitude of variables, from soil composition and climate to the specific variety of seed used. Traditional agricultural experiments, often conducted on a large scale, were expensive and time-consuming. Gosset, operating within the constraints of the Guinness brewery, needed methods that were both efficient and effective. He recognized that the key lay in carefully designing experiments to minimize the influence of confounding variables, factors that could obscure the true effects of the treatments being studied. His solution involved a sophisticated understanding of experimental design principles, particularly the use of randomized block designs. These designs involved dividing the experimental field into blocks, each representing a relatively homogeneous area. Within each block, different treatments, such as different varieties of barley or different fertilizer applications, were randomly assigned to plots. This approach allowed Gosset to control for spatial variability, as any differences between blocks were accounted for in the analysis. The randomization of treatments within each block ensured that any remaining variability was distributed randomly, thereby reducing the risk of systematic bias. A concrete example of Gosset's work in action can be found in his experiments to assess the impact of different barley varieties on the brewing process. He would carefully select a range of barley types, grow them under controlled conditions, and then analyze the resulting malt. The malt's characteristics, such as its extract yield and diastatic power, were crucial determinants of the beer's quality. By using randomized block designs, Gosset could accurately compare the performance of different barley varieties, even when growing them in fields with varying soil conditions. This work directly informed the brewery's decisions about which barley varieties to purchase and cultivate, leading to improvements in the consistency and quality of Guinness stout. Gosset's methods were not limited to randomized block designs. He also employed other techniques to enhance the efficiency and reliability of his experiments. He was a pioneer in the use of Latin squares, a design that allowed him to control for two sources of variation simultaneously. A Latin square is an arrangement of treatments in a square grid, where each treatment appears only once in each row and each column. This design is particularly useful when there are two factors that could influence the results, such as row and column effects in a field trial. For instance, in a brewery-related experiment, Gosset might use a Latin square to assess the impact of different malting processes on the quality of the malt. The rows could represent different kilning temperatures, while the columns could represent different sources of barley. By using a Latin square, he could isolate the effects of both killing temperature and barley source, minimizing the impact of confounding variables. This meticulous approach allowed him to identify the optimal malting conditions, leading to improvements in the consistency and flavor of the beer. The impact of Gosset's experimental designs extended beyond the immediate practical benefits to Guinness. His work played a significant role in the development of agricultural research methods more broadly. His emphasis on careful planning, randomization, and the control of confounding variables became standard practice in agricultural science. His innovations, though rooted in the specific context of brewing, directly influenced the design of field trials for a range of crops, from wheat to potatoes. Gosset's methods also had a direct influence on the emerging field of industrial experimentation. His work demonstrated the value of statistical methods in optimizing production processes and improving product quality. The principles he developed, such as the importance of replication and the use of control groups, were readily adaptable to industrial settings. His focus on practical applications and his ability to translate statistical theory into actionable insights set a precedent for the application of statistics in industry. Furthermore, Gosset's approach was characterized by a constant drive to improve and refine his methods. He was always seeking ways to reduce variability and increase the precision of his experiments. His meticulous attention to detail and his commitment to ensuring the reliability of his results were hallmarks of his work. This dedication to rigorous methodology directly influenced the work of other statisticians and scientists who recognized the value of his innovative approaches. The challenges Gosset faced, particularly the limitations imposed by small sample sizes, forced him to develop methods that were both efficient and powerful. He understood that in many real-world situations, it was often impossible to collect large amounts of data. His work on the t-distribution, combined with his innovative experimental designs, provided the tools needed to make sound inferences even when working with limited resources. The specific problems these designs helped solve were varied, yet consistently aimed at reducing variability. For example, in the context of malt quality, the Latin square designs helped to minimize the effects of variations in barley source and kilning temperature, leading to a more consistent product. In field trials, his methods helped to account for spatial variability, ensuring that the results accurately reflected the impact of the treatments being studied. This focus on reducing variability was crucial for improving the consistency and quality of Guinness stout. Gosset's work on experimental design, therefore, represents a pivotal contribution to the development of modern statistical methods. His innovations addressed the practical challenges of agricultural research, but his methods proved to be universally applicable. His legacy is reflected in the widespread use of randomized block designs, Latin squares, and other experimental techniques across a wide range of scientific disciplines. His emphasis on practical applications and his ability to bridge the gap between theory and practice continue to inspire researchers today. William Sealey Gosset's contributions, viewed in their totality, reveal a profound impact on the trajectory of statistical science. The t-distribution, born from his meticulous analysis of small samples, remains a cornerstone of statistical inference. Its enduring relevance is a testament to the power of his insights. This distribution provides a robust framework for hypothesis testing and confidence interval estimation, particularly when dealing with limited data. This is a situation encountered frequently in fields such as medicine, where clinical trials often involve relatively small patient groups, and in the social sciences, where data collection can be costly and time-consuming. The t-test, a direct application of the t-distribution, is a ubiquitous tool in modern statistical software software packages utilized across a multitude of scientific disciplines. From analyzing the effectiveness of new pharmaceuticals to evaluating the impact of educational programs, the t-test provides a rigorous method for determining the statistical significance of observed effects. Gosset's empirical approach, a hallmark of his work, is a lesson in the importance of grounding theoretical advancements in practical realities. His work emerged from the specific needs of the Guinness brewery, yet its significance transcends the confines of brewing science. His ability to translate real-world problems into mathematical formulations and then to devise solutions that were both elegant and practical distinguishes him as a pioneer in applied statistics. His focus on the practical challenges of agricultural research, for instance, yielded universally applicable methods. Randomized block designs in Latin squares, developed to address the complexities of field trials, found applications far beyond the agricultural sector. These techniques are now standard practice in experimental design across a wide range of scientific disciplines, allowing researchers to control for extraneous variables and to draw more reliable conclusions from their experiments. The influence of Gosset's work extends to the very structure of modern statistical thought. His focus on small sample inference marked a critical transition. Prior to his contributions, statistical theory largely relied on large sample approximations. The central limit theorem, for example, provided a powerful framework for making inferences about populations based on large samples. However, in many real-world scenarios, large samples are simply unattainable. Gosset's work offered a solution to this limitation, providing a means to draw valid conclusions even when dealing with limited data. This shift in perspective, from a reliance on asymptotic theory to methods applicable to small samples, redefined the scope and applicability of statistical methods. This, in turn, expanded the use of statistical analysis across a wider range of scientific and practical contexts. The unique circumstances of Gosset's research, conducted within the constraints of his employment at Guinness, further illuminate his dedication to scientific inquiry. The policy of anonymity, which required him to publish under the pseudonym student, presented unique challenges. Despite these limitations, his work flourished. The fact that he was able to make such groundbreaking contributions while working in a corporate environment underscores the power of intellectual curiosity. It highlights the potential for innovative research to emerge from unexpected sources. His ability to navigate these constraints, to publish his work, and to engage with the wider scientific community is a testament to his resilience and his unwavering commitment to advancing statistical knowledge. The influence of Gosset's work is reflected in the subsequent development of statistical methodology. His insights directly influenced the work of Ronald A. Fisher, a towering figure in the history of statistics. Fisher, in his seminal work Statistical Methods for Research Workers, incorporated and expanded upon Gosset's t-distribution in his experimental design techniques. Fisher's work, in turn, had a profound impact on the development of modern statistics, solidifying the importance of Gosset's contributions. Fisher's adoption and refinement of Gosset's methods helped to disseminate his ideas more widely, ensuring their integration into the standard toolkit of statisticians and researchers. Furthermore, Gosset's emphasis on the importance of understanding the underlying assumptions of statistical tests continues to be relevant. He understood that the validity of statistical inferences depends on the careful consideration of the data and the context in which it was collected. This emphasis on critical thinking and careful interpretation is a defining characteristic of his approach. It serves as a valuable lesson for researchers today. The t-test, for example, assumes that the data are approximately normally distributed. Gosset's work underscored the importance of verifying this assumption before applying the test. Otherwise, the results could be misleading. This focus on the careful application of statistical methods and on the importance of understanding their limitations is a critical part of his legacy. Gosset's approach to statistical innovation was characterized by humility that belied the profound impact of his work. He was driven by a desire to solve practical problems. He never sought personal acclaim or recognition. His focus was always on the science. This dedication to solving real-world problems and his willingness to share his insights with others helped to foster the development of the field. His collaborative spirit is evident in his correspondence with Fisher and other leading statisticians of his time. This collaborative approach fostered a dynamic exchange of ideas that accelerated the advancement of statistical knowledge. In conclusion, William Sealey Gosset's work represents a pivotal moment in the history of statistics. His development of the t-distribution and his pioneering work in experimental design transformed the way we analyze data and draw inferences. His methods, born from the practical needs of the brewing industry, have found widespread application across a multitude of scientific disciplines. Gosset's empirical approach, his ability to bridge the gap between theory and practice, and his unwavering commitment to solving real-world problems cemented his place as a key figure in the development of modern statistical methods. The enduring relevance of the t-test, the widespread use of his experimental designs, and the influence of his work on subsequent generations of statisticians all testify to the profound and lasting impact of his contributions. His legacy reminds us of the importance of addressing practical challenges with statistical innovation. It underlines the value of rigorous analysis and the power of empirical inquiry in advancing scientific knowledge.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.